네, 박건우 씨 안녕하세요. 한성민 씨 안녕하세요. 네, 정상목 씨 안녕하세요. 자, 그래요. 그러면은 숙제하는데 혹시 어려움 같은 게 있었었나요? 자, 먼저 그 얘기를 듣고 시작을 하도록 하겠습니다. 네, 한성민 씨 질문을 하시죠. 박건우 씨 제가 잘 이해를 못했는데 샤페터 구매 스킴을 사용하지 않아도 되는 거요라는 게 무슨 얘기죠? 샤페터 구매 스킴을 당연히 쓰셔야겠죠? 네, 당연히 쓰셔서 혹시 뭐 예전에 그러니까 우리가 처음에 막 중간 과정으로 내고 그랬을 때 샤페터 굿맨 스킨 뭐 안 쓰고 해보자 이렇게 얘기를 했었던 것 때문에 그러는 거라면 그거는 어디까지나 중간에 여러분들이 구현을 좀 편하게 해보라고 하는 것이지 계속 그래야 되는 건 아니죠. 네, 그러니까 당연히 박건우 씨의 질문의 대답은 포텐셜 차이가 크건 작건 언제나 샤페터 굿맨 스킨을 사용해야만 합니다. 네, 그게 답이 될 것 같고 한성민 씨 같은 경우에는 그게 무슨 소리죠? 스몰 시그널을 풀 때 DN, DP, D5 그렇죠? 델타 N, 델타 P, 델타 P는 한번 매트릭스 방정식을 풀면 풀 수 있죠. 그런데 그 다음 문장을 그 다음을 이해를 못 하겠어요. NP5는 왜 한 번으로 풀 수 없냐? 라는 말이 거기서 말한 저 N하고 P하고 P가 어떤 건가요? 네, 한성민 씨, 당연히 비선형성이 있으니까 풀 수가 없죠. 한성민 씨가 고려하고 있는 델타 N과 델타 P와 델타 P로 이루어진 그 시스템은 선형화가 된 시스템이기 때문에 선형 시스템은 한 번 풀어가지고 얻어낼 수가 있죠. 하지만 N과 P와 P로 이루어진 우리의 드리프트 디퓨전 모델은 원칙상으로 비선형 시스템이기 때문에, 그렇기 때문에 당연히 한 번으로 풀 수가 없고, 그걸 선형화를 시킨 그런 뉴턴 랩슨 메소드를 사용을 해가지고 여러 번에 걸쳐가지고 근사적인 해에 다가가게 되는 거죠. 네, 정상목 씨의 질문부터 먼저 답을 할게요. 여기 이렇게 G에 알파하고 베타가 있다고 생각을 합시다. 그리고 여기서 알파나 베타는 모두 파이가 될 수 있고 n이 될 수 있고 아니면 p가 될 수 있는 이런 상황이죠. 여기서 알파는 뭐냐면 이퀘이션의 인덱스예요. 아니요, 거꾸로죠. 알파는 관찰하는 베리어블의 인덱스고, 베타는 이퀘이션의 인덱스입니다. 그래서 한번 볼까요? 정상목 씨가 G, N, Phi의 물리적인 의미가 이해가 안 된다 라고 말하면, 이건 뭐냐면은 포화송 이퀘이션에 퍼터베이션을 넣고 그 다음에 일렉트론 덴시티를 관찰을 한 것입니다. 그 다음에 뭐 말한 것처럼 G, P, Phi라고 한다면 이건 역시 포화송 방정식에다 소스를 넣고 그 다음에 홀 덴시티를 관찰을 한 겁니다. 따라서 이거랑은 전혀 의미가 다르죠. G의 phi n하고는 다르죠. 이건 일렉트론 컨티뉴이티 방정식에다 소스를 넣고 대신 관찰을 일렉트로스테릭 포텐셜을 관찰을 한 것입니다. 네. 자, 안성민 씨의 다른 질문을 한번 볼까요? 더블 게이트 모스펫 구조 또는 어드미턴스를 계산을 할 때 어널리틱 솔루션은 동일하게 논문에서의 식을 사용을 하면 되나요? 이게 무슨 얘기죠? 논문에서의 식이라는 게 어떤 거죠? 더블 게이트에 대해 가지고 우리가 어널리틱 솔루션을 가지고 있나요? 제가 기억하고 있기로는 우리가 어널리틱 솔루션을 유도를 한 건 1차원 시스템의 호모지니어스한 바만 했던 것 같습니다. 자, 그리고 박건우 씨 질문. AC 계산에서 주어진 이전 렉처의 수식. 수식이라고 말하는 게 뭐죠? 혹시 뭐 호모지니어스한 바에 대한 결과라고 한다면 그렇게 하나 저렇게 하나 별 차이 없을 거예요. 그러니까 제가 굳이 여러분들한테 뭐 샤페터 군멜 스킴을 써서 하는 거를 해보라고 하지 않은 이유는 그게 너무 당연한 거고요. 당연하기 때문에 말씀을 안 드렸던 거고, 네. 만약 여러분들이 그걸 이제 검증을 그렇게 하지 않았다면 하도록 하십시오. 숙제로 나가지 않더라도 당연히 하셔야 되는 거죠. 네. 자, 또 다른 질문이 있을까요? 자, 근데 지금 여러분들의 질문 수준을 보면, 네, 일단, 투포트와 같은 쓰리포트가 뭐죠? 자, 일반적으로 우리가 만약에 어떤 N터미널 디바이스를 가지고 있다고 생각을 해볼게요. 터미널의 개수가 3개라고, 뭐 3개든 N개라고 생각을 해보도록 하죠. 이렇게. 뭐 1번, 2번, 3번 해가지고, 네. 네, 이렇게 돼 있다고 생각을 하면 우리가 요거에 대해서 Y 파라미터를 결정을 할 수 있는데 이것도 역시 알파하고 베타라고 이렇게 써볼 수가 있겠네요. 여기서 알파하고 베타는 이제 숫자가 될 텐데 1에서부터 어디까지 바뀔 수 있는 거냐면 n까지. 그러니까 3터미널이라고 한다면 3x3가 되겠죠. 알파하고 베타가 모두 1에서부터 3까지 바뀔 수 있을 테니까. 근데 이거는 어떻게 정의가 되냐면 이렇게 정의가 된다고요. 라운드 I 알파 오버 라운드 V 베타. 요게 데피니션입니다. 물론 이건 편미분이니까 현재의 동작 조건을 생각을 해줘야겠죠. 현재 이 소자가 어떤 상태에 있다라는 걸 가정한 상태에서 이렇게 계산을 해주는 겁니다. 그러니까 박건우 씨의 질문을 제가 잘 이해를 못 하겠는데 만약에 이거를 디바이스 시뮬레이션 코드를 짜서 Y 파라미터를 구성을 하고 싶다면 그렇다면 요 정의에 따라서 이런 일들을 해줘야겠죠. 그러니까 무엇을 할 수 있냐면 처음에 V1은 델타 V1은 유닛인 상황에서 델타 V2하고 델타 V3는 모두 0인 조건을 물론 여기서 말하는 건 이렇게 해야겠죠. 이때 어떤 가정이 있냐면은 다른 모든 델타 감마들은 0입니다. 그래서 이때 감마는 베타하고는 다른 녀석들에 대해서 모두 다 0으로 놓고 그러니까 이렇게 생각을 해볼까요? 어떤 거냐면 제가 3번 터미널에 이렇게 소스를 볼티지 소스를 넣어주면 나머지 애들은 어떻게 해야 되느냐? 다크그라운드 해야 된다는 거죠. 이렇게. 자, 이렇게 됐을 때 다시 여기로 돌아가서 디바이스 시뮬레이션 코드를 짜면서 Y 파라미터를 구하는 방법은 이와 같은 경계 조건을 놓고요. 전압 조건을 원하는 터미널에만 유닛 익사이테이션을 주고 나머지 애들은 다 0으로 놓은 다음에 그렇게 한 상태에서 우리가 다시 뭘 계산할 수 있을 거냐면 델타 I1, 델타 I2, 델타 I3를 구할 수 있을 거예요. 자, 그리고는 얘네들 사이의 레이쇼를 구하게 되겠죠. 이렇게 델타 V1, 델타 V2, 델타 V3 하게 되면 이들 각각이 어떻게 잠깐만요. 자, 말을 잘못했네요. 여기서 지금 현재는 V1을 바꾼 상황이니까 여기선 V1, V1, V1이 될 거고, 그러면 이들 각각이 어떤 파라미터에 해당할 거냐면 Y11, 요거는 Y21, 그리고 요거는 Y31에 해당할 것이다. 이렇게 해서 구하실 수가 있을 겁니다. 이게 이제 Y 파라미터를 구하는 방법이 되겠죠. 자, 그런데 박건우 씨의 원래 질문은 뭐죠? 네, 요게 이렇게 구해주는 겁니다. 예. 수업 시간에 설명을 했었던 내용이고요. 그렇지만 질문해 주신 거는 이해가 안 되면 당연히 질문을 하는 게 맞겠고요. 자, 그래요. 다른 질문들 있으신가요? 자, 그런데 여러분, 제가 여러분들의 질문을 듣다 보니까 사실 우리가 지난 시간에는 네, 얘기하시죠. 네. 네, 그렇죠. 그린 펑션의 결과는 사실 해석하기가 간단하지 않습니다. 네, 맞습니다. 거기서 나오는 결과는 그린 펑션을 풀게 되면 벡터들이 나타나게 될 거예요. 솔루션 벡터가 나타나게 될 거고, 그렇죠. 그래서 거기서 나타나 있는 그린 펑션 중에서, 그러니까 예를 들어서 우리가 어떤 방정식에 뭘 건드렸는지와 관계없이 이런 값들을 여러분들이 얻게 되실 거예요. 이렇게. 도대체 이게 뭐지? 라는 생각을 할 수 있겠죠. 자, 그런데 이제 전자농도 같은 것들을 생각을, 이건 이렇게 생각을 해볼 수가 있겠죠. 얘네들이 각각 phi하고 n하고 p하고가 관찰하는 것이라는 건 알 텐데, 여기가 이제 어떤 거냐에 따라서 물리적인 의미를 바꿀 수가 있을 겁니다. 예를 들어서 이게 만약에 이 뒤에 붙어 있는 이퀘이션 인덱스가 phi인 경우를 생각을 해볼까요? phi인 경우를 생각을 한다면 이것은 포화송 방정식에 우리가 소스를 집어넣은 거죠. 그런데 포화송 방정식을 한번 생각을 해보세요. 포화송 방정식이 어떤 식으로 생겼는지, 포화송 방정식에 들어가는 소스라는 것은 사실 우리의 뭐 꼬리에 어떻게 쓰느냐에 따라 다르겠지만 넷 차지 덴시티에 해당하는 걸 겁니다. 그러니까 이 그린 펑션 중에서 이 그린 펑션 중에서 이퀘이션에 phi가 들어가는 형태는 결국은 우리가 어떤 지점에 점전화를 이렇게 각 주파수 오메가를 가지고 넣었다가 뺐다가 넣었다가 뺐다가 넣었다가 뺐다가 하고 있다는 거고요. 그에 따라 가지고 우리의 전자농도, 홀농도, 포텐셜이 어떻게 반응하는지를 관찰하는 것이다. 이렇게 표현을 할 수가 있겠고요. 만약에 전자농도 일렉트론 컨티뉴이티 이퀘이션에다 이걸 집어넣는다 라고 한다면 이거는 그 방정식을 생각을 해보시죠. 그건 컨티뉴이티 이퀘이션은 한 지점에서의 전자농도의 시간 변화량을 뜻하는 거잖아요. 근데 거기에 전자농도를 집어넣다가 전자를 집어넣다가 뺐다가 집어넣다가 뺐다가 그 어떤 각 주파수 오메가를 가지고 넣었다가 뺐다가 하는 것은 결국은 전자를 특정 지점에 우리가 보고 있는 지점에 대해서 전자를 넣었다가 빼줬다가 넣었다가 빼줬다가 이렇게 하는 것에 해당하게 되어 있습니다. 결국 그 말은 뭐냐면은 전자가 하나가 더 뭐 모스펫 같은 걸 생각을 해보세요. 모스펫이 있어가지고 걔네들이 이제 세츄레이션 모드에서 동작을 하고 있습니다. 근데 그때 만약에 우리가 어떤 채널에 있는 어떤 점에다 전자를 하나를 추가적으로 집어넣었다고 생각을 해보세요. 그러면 어떤 일이 생길 것인가? 그러면은 이 녀석은 당연히 오른쪽이든 왼쪽이든 그러니까 소스 쪽이든 드레인 쪽이든 움직일 텐데 아마도 세츄레이션 영역이라면 얘네들의 에너지 밴드 프로파일 같은 것들이 드레인 쪽으로 심하게 기울어져 있겠죠. 그러니까 그렇게 되면 아마도 드레인 쪽으로 전자들은 이동을 해가지고 거기서 이제 컨택을 통해서 드레인 컨택을 통해서 빠져나가게 될 것입니다. 그래서 이럴 때 얻어지게 되는 GN 값 같은 경우는 바로 우리의 전자가 거기에 인젝션이 되고 그에 따라서 전자들이 어떻게 흘러가는지를 나타내는 그 모습, 흔적을 나타낸다고 할 수가 있고요. 그때의 포텐셜 같은 경우에는 전자가 하나 더 들어갔기 때문에 주변에서 바뀌게 되는 포텐셜의 변화 같은 것들을 나타낸다고 할 수 있죠. 홀에 대해서도 마찬가지가 되겠고요. 그렇게 생각을 해주시면 될 겁니다. 하지만 어쨌든 해석 같은 거는 사실은 그렇게 간단하지는 않죠. 자, 번호 C의 질문은 아주 좋은 질문이었고요. 네. 자, 그런데 제가 계속 하려고 했었던 말은 뭐냐면, 그런데 건호 씨의 마지막 질문을 제외하고는 사실 여러분들의 질문이 다 아직 AC 시뮬레이션에 머물러 있는 것 같아요. 지금 우리는 어떤 걸 배우고 있냐면 그린 펑션을 배우고 있는데 그린 펑션에 대한 질문이 좀 부족하다는 생각입니다. 그래서 여러분들이 과연 그린 펑션까지 잘 구해내고 있는 것인가 라는 게 사실 파악이 잘 안 되네요. 자, 그렇기 때문에 여러분들이 이거와 관련해 가지고 더 작업을 해 주셔야 된다 라는 얘기를 하고 싶고요. 추가적으로 더 질문이 없으면 오늘의 강의를 시작하도록 하겠습니다. Okay, so this is lecture 21st. So we will start from our previous lecture content, the green function. Yes, in the previous lecture we have introduced a certain quantity called green function. So it has two indexes for alpha and beta, and of course it can have r and r prime. So or not whatever. So here, so physical meaning of this one is we introduce or source term Dirac delta at r minus r prime in the equation beta. Okay, then we observe the response of the solution variable alpha. So simply speaking, that is the definition of our green function sub alpha and beta. So once again, this is variable index and this is equation index. Okay. So actually by getting this quantity you have full knowledge on your system. So now you understand not only the terminal excitation but also the internal excitation can be considered by your analysis. So for example, you can think about your y parameter, and then this is corresponding. Of course, this alpha and beta is not related with this variable in equation set. This is just terminal indices. Yes. However, anyway, this y parameter is related with the response of your system with respect to the voltage excitation applied to the terminal beta. And now this green function is once again the response of your system with respect to the excitation at the equation beta at position r prime. So now everything is quite easy and simple. So in principle, everything is easy and simple. But you know that, so think about this one. Usually, let's make a good comparison between this green function and y parameter. So this is a certain expression for our green function, and I wanted to talk about another quantity called y parameter. So y parameter also we have alpha and beta, but you know that we have very much different information. So think about this one. If I write down r, is it correct? No, we don't have any position dependence in y parameter. Why? Why we don't have such kind of position dependent? Because you know this is terminal index, as I told you before, and this is another terminal index. So y parameter is just terminal to terminal relationship. Okay, so let's consider an arbitrary shape, and now we are saying that y parameter simply means that if I excite at this terminal, then what will happen to this terminal? That is the information obtained from this y parameter. Yes, so please note that y parameter is just a relation between terminal to terminal relation. That sounds just too obvious. However, let's think about this g, green function. What we have done in this case is, let's say that this is happen to be the position r prime. Now what is it? What we have done up to now is, now of course, instead of this excitation, now we have to say this terminal is also AC grounded. Yes. Then what we have done in this green function calculation is, now we insert a certain excitation inside our system and just to measure the response of our physical quantities. Okay, let's say that this is the isosurface of something. So think about this one. Yes. So maybe the Mr. Park has observed such kind of behavior, and he felt it was difficult to interpret its physical meaning. Yes, yes, that's okay. So that is the situation. So my question is, just to assume the case, voltage excitation or internal excitation, and in this sense, please make a comparison of the level of information. So green function, how detailed is it? And y parameter, or admittance, how detailed is it? So can you make a comparison? So basically, both of y parameter and green function just consider a single excitation, whether that is appearing in the boundary condition or that is appearing in the perturbation inside one single equation. They are different, but anyway, there is one single excitation. And what is observed in this y parameter and what is observed in this green function? So please make a comparison. In this case, we observe, in the case of y parameter, we just observe terminal current. And terminal current is a scalar quantity. Then think about this green function. How about this? In this case, we just observe variable alpha, and this is position dependent scalar field. Okay, so you know that now green function in this form is much more detailed than this this y parameter. So simply speaking, green function just to observe everything. So every change in your electrostatic potential, electron density, hole density, those changes are just memorized in this green function. Instead of that, this y parameter just to neglect all kinds of detail and just to select one single number. So how much the terminal current is changed, that is measured by the y parameter. So now you can understand they are very much different in the level of description. So y parameter is much more simplified, and yes, also green function is much more detailed, actually contains full information about our system. So that's good, that is so good. However, if our interest is just terminal quantity, then maybe we want to build a quantity which is close to what? To y parameter. So instead of this g sub alpha beta, where variable is observed, instead of that, we can try to build such kind of quantity. So now let me just introduce something like this. G, for example, I and alpha and beta. Yes. And now having only one single position dependence. So can you understand the difference between this upper description and lower description? So although I have used the same Greek alphabet, alpha here, but please note that this is a variable. It can be phi, n, or p. And this alpha is a terminal, so it can be, for example, source, gate, drain. Okay, so once you understand the first index becomes a terminal index, now you understand the missing R here. Why we don't have R here? Because our observation quantity is no longer position dependent scalar field. It is just a number, scalar number. So now we have only position dependency originated from our source. So of course, once again, our equation beta is perturbed at the position of r prime. Yes, but that will generate all kinds of reaction or responses of our variables. So that will just given as g phi beta, gn beta, and gp beta. So from these responses, of course, we can calculate delta of I sub alpha. So for example, we can calculate the fluctuation of drain current. Then that can be just measured. And once you measure this one, then that is corresponding to our G sub ID beta. Okay, so I wanted to ask to my students about whether you have, all of you have understood this difference between the green function in its general form and the form specialized for the terminal quantity. Although both of them are called as green function, but they are very much different. Of course, which one is fundamental and which one is just a derived one? Of course, the upper one is fundamental one, and the lower one, the terminal green function, is just a certain combination of our general green function. But anyway, that gives us much simplification than the previous one. So it has two indices, and now we have only one index. So it means that previously we have to calculate a matrix, and now we can, it is enough to calculate only a vector. Okay, so please check whether all of you have understood my explanation. So only after you give me the feedback, I can proceed further. Okay, so thank you, Mr. Han. So I have used, for example, same alpha here, so that can introduce certain confusion in this case. We don't have to use the same one. So why don't you just say gamma? So this is corresponding to, for example, in the case of MOSFET, source current, drain current, or gate current. And this alpha can be physical quantities like potential, electron density, and hole density. So I have used the same alpha, so same notation, but we don't have to do that. So we can use different quantities. But point is in these two cases, or typical example is, yes, typical example is phi, and this is the physical meaning of this quantity is electron continuity equation is perturbed, and we have observed the response of electrostatic potential. And yes, this means that the perturbation is the same, and instead of that, we just observe drain current. Since this electrostatic potential is a position dependent one, we have to consider the response of the electrostatic potential at different positions. However, in the case of our terminal Green function, since this quantity is a scalar number, so it is quite easy to get just one single number. Yes. Okay, so now once you understand the difference between these G green functions, your feeling about this green function is like this. Okay, which one is more fundamental? Yes, upper one is fundamental. However, in practical purpose, they found that, they means that engineers found that it is enough to just have this lower one, terminal current green function. So this quantity is enough for our purpose. Good. That is the thing we have done. Okay, so depending on the literature, we have many different notations for this quantity. For example, in many cases, since this terminal current is understood, so for example, we just neglect this I. So typical notation we can find in the literature is like this. So what is it? It is just in our notation, in below notation, it is just G sub ID, comma, N. So whether that is superscripted or subscripted or I is omitted or not, yes, there can be many different ways to think about this quantity, but anything is just okay if that is written in a consistent way. So so yes, so I will just follow the more widely adopted notation here. Then please note that this is nothing but, let me just repeat again, what is the meaning of this quantity? So what is the meaning of this quantity R prime? So it simply means that we introduce a source term in the electron continuity equation at a position R prime. Then we observe small variation of the drain current. That is the physical meaning of this quantity. Of course, you can define many different, many similar quantities like G sub source or so sorry about that. I made mistakes about upper and lower or superscript and subscript. So the more widely used one is here and there. Sorry about that. So we can think about this quantity or that quantity. Another quantity we can find is, yes, for example, drain for phi. And yes, you can find many different ones like phi and source phi. Also, you can copy another copy related with P excitation. Okay, so do you have any question about this terminal current green function? Of course, when you write down in this way, you just say that this is corresponding to your delta ID. So terminal current is understood. Yes. So, however, that is so widely used. So I think that in my opinion, we can assume the terminal current as a understood observable quantity. Okay. Good. So, for example, now we can say this way. One of the most important Y parameter in our MOSFET is, for example, YDG. So, is it difficult to say so, since that really depends on the context. So that really depends on the context. So please check what is the observable variable in your paper. So the paper you have read. So So I have no idea about that. Then what is the leakage current in your case? That is the main thing you have to understand. So which terminal current is defined as the leakage current? So please check that point. If the drain current is regarded as the leakage current, then you are right. But if substrate current is regarded as leakage current, then you have to say that this is corresponding to the substrate. So that is really depends on the situation. No, so depending on the authors, they have used different notations for this quantity. So please check it. Yes, so I think that actually Mr. Park, his work is really closely related with this green function. So maybe he will find that the theoretical background for his research work. So, now let's consider the typical or most representative example of Y parameters and green functions. For example, YDG is a kind of a transconductance-like quantity, we have applied the voltage excitation to gate and observe the change of our drain current. And also we can think about this quantity. Yes, once again D, and yes, this quantity can be found. What is it? Still, we observe change of drain current, but instead of gate voltage excitation, now we introduce a Dirac delta source term into our electron continuity equation. So, please note that this is corresponding to voltage excitation. And this is corresponding to the insertion, or more frequently they say injection of electrons. Yes. So we just inject electrons by certain means to somewhere and observe the behavior of our system. And another quantity, of course, we have a whole quantity, and they are related in a similar way. And we have another important quantity like this. This is a little bit different. So although observation quantity is still drain current, but in this case the perturbation is introduced in the Poisson equation, then this is the effect of net charge density. So this quantity can be easily used for analysis of that one. For example, if we have certain device, but by the variation of this system, let's think about this one. Now we have a transistor. Yes, and transistor, we have the DC characteristics. Good. But by the imperfection of our doping, let's say that happen to be we have more impurities here, then what will happen to our drain current? So you can easily understand, since we have introduced additional dopants, p-type dopants here, then threshold voltage will be locally a little bit increases, and here part is more closely placed to source and drain. Let's assume in the left one is source and right one is drain. Then that can affect our drain current in a negative way. So since the source part is affected by in the direction of higher threshold voltage, so we can observe that drain current will be decreased according to the introduction of additional net charge density. That can be considered by this function, green function, where the perturbation is inserted in the Poisson equation. Okay, so Mr. Park and or other students, so can you understand this situation? So if we have any dopant imperfection or dopant variation, that will be appeared in the Poisson equation, and the response of our system with respect to the Poisson distribution or perturbation in the Poisson equation can be described by this simple function. Of course, if our ultimate interest is on the drain current, then we can use it. So another example of this Gn is like this. So here, let's say that here we have a certain point which is quite having quite many SRH center. So SRH means that Shockley lead hole, naming from three important contributors, and it is a recombination center. So recombination center means that if electrons holes are there, they can recombine, and simultaneously their density can decrease and approach to the equilibrium value. Or if there is no electron and no hole at all, in this case this SRH center can be a source of electron hole pairs. So it can, so SRH recombination center can generate electron hole pairs. So SRH center is nothing but just the origin of our generation recombination inside our system. In this case, yes, what will happen by this recombination center? Then let's consider certain depletion region where we have no electron at all. Yes, for example, let's think about certain range. Yes, and this is really depleted. No electron, no hole. In this case, our SRH center will used as the source of generation. So what will happen is, in this case, we will have the generated electron and generated hole at this point. So from the viewpoint of the electron continuity equation and hole continuity equation, each continuity equation has one additional electron or hole generated by our SRH recombination center. Then the generated electron or the generated hole, to them, what will happen? That can be well described by this G sub n or G sub p. So now you understand, depending on the situation of your perturbation or imperfection from this clean and ideal device, you have to use the proper green function. So I think that is typical examples you can see in your study about the electronic system. Okay, if you have any question, then please let me know. So I think that if you have all of you understood the lecture contents up to now, I guess that you will love this function. Okay, if I can have this function, then maybe I can directly calculate many important terminal quantities. Also, in many cases, we are only interested with terminal quantities, so details inside our system, yes, can be just neglected. Neglected means that they are always there. However, we don't want to check them, just to check our terminal responses. So maybe you will like it very much, and now you wanted to calculate it. So I think that today we have just a simple, really simple homework. So I assume that all of you have done homework 20. If you have not done it properly, then please catch up the homework progress. After that, please, in our homework 21, please calculate your terminal current green function. That is the goal of our homework 21. So maybe you can ask me, then how can I calculate the terminal green function? So it is quite easy. You know that terminal current is just a combination of the quantities nearby the terminal. So by solving the green function, you have a full knowledge about your electrostatic potential, electron density, and hole density by just using these quantities in just the same way with typical quantity. You can calculate the terminal current. Then the calculated terminal current will be called as a terminal current green function. Okay? So my suggestion is think about certain device. Yes, your device can have multiple terminals, and just keep a position for your perturbation. Yes, this is your R prime. Then also you must select your perturbation. For example, perturbation beta can be either phi or carrier. So just perturb it, then you can generate the response of your system. Of course, that will be called as G alpha beta, and by using this G alpha beta, please calculate the terminal current for your terminal 1, and that will called as your terminal 1 and beta, and calculate another one that will called terminal 2 beta. Also calculate terminal 3 beta. So for same position and same equation, you can define multiple quantities like this one, and this one. If you have a 4-terminal device, then you will have 1, 2, 3, 4. If you have a device with 10 terminals, then you will have G1, G2, G3 up to G10. Yes, so you can find many quantities, and anyway, please calculate these terminal green functions. You will find that they are quite interesting. Of course, once you have calculated this one, then you can change your R prime here or R prime there. You can change many different R prime point, then measure the quantity. Okay. So I wanted to give you a simple hint for this quantity. So if you wanted to do it easily, then my suggestion is first consider Gn quantity. Yes, because you know that G phi, this will introduce a little more difficult to you. So first of all, just think about this Gn. Then now if you say I will calculate Gn, then you can, for example, if you are working with a transistor, 3-terminal transistor, then maybe you can have a source, gate, and drain. So you can calculate 3 quantities. And the physical meaning of this is like this. Yes, you have a transistor, gate, source, and drain, and you just insert a certain electron in this position. Then what will happen to this electron? So if you insert your electron just nearby source, then what will happen to this electron? This electron more or less fully just swapped by this source. But think about this guy. If your electron injection is appearing at the drain part, then there will be almost no way for this electron just to go against the current flux and reach at drain. So it will almost 100% swapped by this drain. Of course, if we are considering certain intermediate state, then maybe some electrons can move to drain side and some electron can move to source side. If our applied drain voltage is not that high, then maybe we can have certain one. So simply speaking, these green functions, yes, 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 is just to predict the destiny of your electrons injected at a certain position. So if your electron is injected at a certain part, and in average, so 40% of them will swept by certain terminal, the other will be, all other will be swept by other terminal, then that information is appearing in this terminal current green function. So that is a physical meaning. So I wanted to recommend you to calculate this quantity, and in the case of source 1, if injection point is close to source, then that should have a large value. And if injection is close to drain, then instead of source 1, the drain 1 should have a larger magnitude. And of course, if we restrict ourselves to really small, really small or low frequency, then that would be quite small. You know that electron, there is almost no way to make a contribution to our gate current. Of course, we can consider displacement current. However, since we have assumed that the frequency is quite low, so displacement current can be minimized. So I think that is one easy way to check your green function. So the first thing you have to do is not this full calculation of a transistor, and just to consider a simple homogeneous bar, and please try to calculate your green functions for source terminal current and drain terminal current. After that, once you have done it properly, then extend your example to the three-dimensional, or not three-dimensional, three-terminal transistors. Then you will find very interesting result. Okay, so this is the end of lecture 21st. So please give me your question, then I will answer your question. If you have any question, then please let me know. Then I will wrap up today's lecture. Okay. Okay, good. Then see you Thursday. And then bye.